Okay, so here we are practicing with circuits. I think this is week 27, part 3. And the words say this. Two 100 ohm resistors are connected to a 4 volt battery to form a parallel circuit, and the same combination of resistors and battery are connected to form a series circuit. Please find all the information below. So, you are going to draw a series circuit and a parallel circuit with a 24-volt battery and two 100 ohm resistors. So hopefully they look like this. Series circuit means the current passes through both resistors in order to get back to the battery. Parallel circuit meaning the current has a choice of going through one of the resistors and back to the battery, or through the other resistor and back to the battery. So it looks like this. Okay. Next, we will be calculating equivalent resistance of the circuit. So, yeah, we'll just look at this like that. So, for a series circuit, we just add the resistances together. We get 200 ohms. For the parallel circuit, we use that weird reciprocal formula. So 1 over R equals 1 over 100 plus 1 over 100, which is 2 over 100. And hopefully you can cross multiply and get resistance is 50 ohms. Notice that the equivalent resistance of a parallel circuit, is less than either of the resistors. That will always be the case. Sometimes we'll get crazy circuits that, well, it's more than just a parallel thing, so that doesn't really apply, but for now, okay, current through the circuit. So using Ohm's law, V equals IR, we know we can divide the voltage by the resistance, that is the equivalent resistance of the circuit, to find this 1.12 amps. So that's the current that runs through the circuit. Okay, similarly over here, current through the circuit, so we have a voltage of 24 volts, an equivalent resistance of 30 ohms, giving us 0.48 amps. Notice how that is 4 times as much as the other circuit. More current through the parallel resistance circuit, less current through the series. Okay, voltage drop across each resistor. So let's see, from the previous notes we know something. Voltage drop across the resistor. Excuse me, we know that where the voltage is provided by the battery, and as it flows across the circuit, some of it is used up here, and the rest of it is used up here, and then the electrons return seamlessly back to the terminal of the battery. And just a refresher, this would be the positive, this would be the negative, and so we say that the current goes this way. Again, that is conventional current. The reality is that electrons go this way, but we just say that the current goes from the positive to the negative. Okay, back to where we were. So, excuse me, voltage drop across each resistor. What I used was Ohm's law, which we can do frequently. If we know the current through each is 0.12 amps, we can multiply current by the resistance of the resistor, getting 12 volts. So 12 volts dropped across here and 12 volts dropped across here. Lo and behold, those voltages add up to 24 volts. You really might want to get the very last page of the last notes out. There was this compare and contrast graphic organizer that talked about this exact thing, and that would be helpful to, it'd be nice to reference that while we're going through this. So let's see. Alright, so voltage across each resistor, and here we have a parallel circuit. So in a parallel circuit, notice how this resistor is connected directly to the battery. This resistor is connected directly to the battery via wires. So each of them get a voltage drop of 24 volts. So we say 24 volts across each. It is a parallel circuit. Or you could use, so you could have said, this is a little advanced, but if the current through the circuit is 0.48 and it has two equal resistance paths to choose from, each will get half, and so we could have used this as I and multiplied that by R 100. Notice how 0.24 times 100 gives us 24 volts dropped across each. Voltage dropped meaning used up. Okay, what is the current through each resistor? Let's see. Current is 0.12 amps through each. It's a series circuit. So if the current through the circuit is 0.12 amps, it has to go through both. Alright, but here, current through the circuit was 0.48 amps. And so half is going to go this way and half is going to go this way. And we know that because the resistances are the same. If we had a greater resistance, we know less current would go through it. So how did I calculate that? Okay, yeah, we could use Ohm's law. V equals IR, and so we took the voltage drop across the resistor, divided it by the resistance itself, and ended up with 0.24 amps each. Power dissipated by each resistor. So let's see, power equals current squared times resistance. So the current through each resistor times the resistance, 0.144 watts each. And in the parallel circuit, using P equals I squared R, the current squared times the resistance would give us 5.76 watts each. Okay, moving on. Power dissipated by the circuit. So we're looking at this right here. Here I chose to use P equals IV. You know, we could have used either for both of these and it would work. No problem. But current through the circuit, voltage of the circuit, power dissipated by the circuit. So notice how this, we're talking about one specific resistor. Here we're talking about the entire circuit as a whole. And it is interesting, and it makes sense, that we have two resistors and each dissipates 1.44 watts. So the total power dissipated would be 2.88 watts. And it's always going to work out that way. If it doesn't, you know you made a mistake somewhere. Similarly, for the parallel circuit, P equals IV, we got current, we got voltage. Again, this is current through the circuit. This is voltage of the circuit, and this is the power dissipated by the circuit. Notice how this is twice this. Yes. And then a little curveball question, just to refresh our memory on the electron and everything. Number of electrons that leave the battery in 1 hour. So, we know that current is charge per time. So we're going to figure out how much charge leaves the battery. So we know, let's see, Q, we multiply the current by the time. So the current through the circuit was 0.12 amps, and the time, the number of seconds in 1 hour, is 3600. So that gave us 432 coulombs leaving the battery. Wouldn't want to meet that charge in a dark alley, ha ha ha. And we know that one electron has a charge of 1.6 times 10 to the negative 19 coulombs. Coulombs cancel, leaving us with a whole bunch, but to be more specific, 2.7 times 10 to the 21st electrons. Many. Okay, and similarly over here, we have 4 times the current. So at this point, you could be like, hey, it's 4 times the current, and just take your final answer and multiply by 4, and you would have got this. And you could say, good work. Or you can go through that same process, 1728 coulombs, and then convert to electrons and get this. Okay, let's take a look at page 2 where we have a slightly crazy circuit. We like these. Okay, slightly crazy circuit. So we have this and this in parallel, but this is 2 resistors in we have this and this in series, but this is 2 resistors in parallel. So when you have a situation like this, what you can do is kind of take this and break it down. Meaning, think the 500 ohm and the 700 ohm resistor are equivalent to what? So look at this. Okay, 1 over R, 1 over 500, 1 over 700, and we do a little math and we get 291.7 ohms is the equivalent resistance of this jibba jabba right here. So instead of writing this, we could rewrite it as this. Aha! So we're simplifying our situation. We've got some combination that acts as one resistor with the resistance of 291.7 ohms. Notice, please, how the 291.7 is less than either the 500 or 700. That's always the case. So now we have a circuit with 2 resistors, In series, we could simplify even further and say, yo, that is like this. What would I get whenever I add those? Yeah, something like that. Okay, so it's a battery, 12 volts, and a resistance of 691.7 ohms. So, equivalent resistance of circuit, that's what we just found, 691.7 ohms. Current through the circuit, we're using Ohm's law, so I equals V over R, and we got 12 volts divided by 697. Who made up these numbers? Messy. That's okay. We got a calculator. And so we get this 0.0173 amps, and of course these are rounded. So we're going to get a little rounding difference, but that's fine. Okay. What's next? Current through each resistor. Okay, so with these two, current through each resistor and the voltage drop across each resistor, it does get a little different, a little fun, because, yeah, all the current passes through here. So if we're talking about these two in series, all the current passes through here, and all the current passes through this, right? So we found the current through the circuit. But when we talk about current passing through this, part goes this way and part goes this way. And more of it is going to go this way because it's less resistance than this way. But some is going to go this way, some is going to go this way. And then for the voltage drop across here plus the voltage drop across here will equal 12 volts. So let's see what happened with this calculation. So current through each resistor. If we think about it like this, this is what I just said. Each of these gets 0.0173 amps, okay? But it turns out again that this is more complicated than it first seems. So this is kind of a trick right here that many students find very helpful. So we know that there is 0.0173 amps. Oh, my stylus isn't working. Coming in, right? And part goes that way, and part goes that way. The amount of current that goes, we know that more is going to go on the least resistance path, and we know less is going to go in the more resistance path, and it's going to split up in a ratio of, you sort of do the least common denominator, or you add these two. So we're going to have 7/12 of the current go this way, and 5/12 of the current go this way. The 5 comes from this, and the 12 comes from the sum of those. 7 comes from this, and the 12 comes from the sum of those. And this will always work if there's two paths. So this is the fraction of the total current that it gets, and this is the fraction of the total current that it gets. And if we add these two together, it ends up being the current through the circuit. Okay, so that's kind of a trick. The other way we can do this is we have to use the voltage. So we would move down here to the voltage drop thingy and say, alright, for voltage drop, we know the current through the circuit, and we know the current through the resistor, and we know the resistance of the resistor, so we can multiply 2, and we get 0.692 volts for the first resistor. And then for that combination of two, we could either do this, or we could just subtract this from 12, and we're going to get something just like that within a little bit of rounding differences. So for this combination of two resistors over here, and that's this, so we got the 5.08 volts, we could say, well, I know the voltage drop, I know the voltage drop across these is 5.08 volts, so I could use Ohm's law, and the current through it would be voltage divided by resistance, and for this resistor I could do voltage divided by resistance. Lo and behold, the numbers we would get would be the exact same as these numbers up here. So this is the trick. This is kind of the straightforward, find the voltage, use Ohm's law, whatever. Here we just sort of recognizing that less resistance gets more current, and we use a little ratio and multiply. So that's some tricky stuff, but pretty fun, and we're gonna, you guessed it, do lots of practice. So enjoy.